We have taken examples of electron donating groups by inductive effect that increase electron density in the benzene ring, therefore increasing its nucleophilicity and, as a result, enhancing the reactivity of those substituted benzenes in electrophilic aromatic substitution reactions. Let's now take examples of electron donating groups by resonance. So let's see that. This is the benzene ring, and now we should put an atom that can donate electrons, and obviously for an atom to donate electrons it must possess a lone pair. It must have a lone pair. If it doesn't, it would not be able to do so. So something like this, a very general symbol with that lone pair. So that lone pair is actually essential for any electron donating group by resonance, or for any group to behave as an electron donating group by resonance. That lone pair again is essential for such effect. So we are talking here about electron donating groups by resonance. Any atom that has a lone pair can donate electrons to the benzene ring by resonance. So what can we think of examples of atoms that can donate electrons by resonance to the benzene ring? Well, obviously we would think probably intuitively of oxygen, because oxygen has two lone pairs that can therefore act as an electron donating group by resonance. Not only oxygen, nitrogen, for example, it has also a lone pair. Actually, nitrogen is less electronegative than oxygen, therefore it's a beta electron donor. Therefore it's actually a beta electron donating group by resonance than oxygen. So nitrogen, oxygen, any heteroatom basically with a lone pair. So let's take examples of those types. So something like phenol, hydroxy benzene, that oxygen atom has two lone pairs, therefore it's entitled for this donation by resonance. If we take in general amino benzenes, and again nitrogen is directly bonded to this carbon of the benzene ring. Nitrogen has that lone pair, so therefore it can donate electrons by resonance. Not only amino benzenes or hydroxy benzenes or phenols, for example, as commonly described for, or as a common description for hydroxy benzene, but also alkoxy benzene. So this is a general structure for alkoxy benzene. And again, alkoxy benzenes have oxygen atom which has two lone pairs. These two lone pairs, or one of them actually, can be used to donate electrons by resonance to the benzene ring. In all of these cases, the benzene ring is actually more electron rich. It's much more nucleophilic than unsubstituted benzene, and therefore reactivity of all of these substituted benzenes would be much more than unsubstituted benzene itself in electrophilic aromatic substitution. Let's now see how this resonance with donation is actually done by these groups. So this is a general structure of a substituted benzene with a group, if you like, or with an atom that has a lone pair, an atom or a group that can donate electrons by resonance. Let's see how we can do this, or let's see how can this group donate electrons by resonance to the benzene ring. Now we can use a lone pair on this atom to make a double bond here. So something like that, and as a result, obviously, this carbon-carbon double bond must be broken, and the two electrons that are released can now be put on that carbon. So this will give us another resonance form. and obviously a lone pair on this carbon that now has that release pair of electrons. So far, this is actually clear. It's actually clear to us that the electron density in this benzene ring is now more. We can continue to further delocalize electrons on the benzene ring. So if we take that lone pair and now we make a double bond between that carbon and that carbon, we would have to break this carbon-carbon double bond, and now we put the release electrons on that carbon. So let's do that. Obviously, A, or the atom, when it makes a double bond, it should carry a positive charge. You see now, in this resonance form, this carbon has now a lone pair, so we have delocalized electrons further on the benzene ring. We can continue to do so by taking this lone pair and now making a double bond here and breaking that carbon-carbon double bond. This will give us another resonance form. Where the lone pair is now on that carbon. So by these four, we can continue obviously to get another one. Okay, but it's clear enough to us, okay, that electron donating group by resonance has donated electrons to the benzene ring, as shown very clearly by the carbanion, if you like, by the lone pair on these carbons, or the negative charge. So therefore, the electron density on this substituted benzene is actually increased. If the electron density is increased, therefore its nucleophilicity is also increased. If the nucleophilicity is increased, therefore this substituted benzene can behave as a much better nucleophile in electrophilic aromatic substitution reaction. So we can say that also reactivity is also increased. So in summary of this, any atom with a lone pair can behave as an electron donating group by resonance. This electron donation by resonance increases electron density on the benzene ring as shown here. The nucleophilicity is therefore increased, and as a result, the reactivity of this substituted benzene by this electron donating group by resonance is increased in electrophilic aromatic substitution reactions.